So I'm going to start. Good morning. I'm Avidan, GSI Technology. What we are going to talk today is we're talking about on real in-memory computing. So we're going to show how we do compute in real memory. It's not just a simple storage. It's not just a simple storage that we can do compute inside the memory. We call it associative memory. So we'll talk today about what is AI, artificial intelligence, and machine learning a challenge. We introduce associative computing, what it is associative computing. We can show how we can convert a memory cell that can do a compute inside. We show some example and use cases. And also, we talk about the NLP, natural language processing use case, and also show you the roadmap for next. So when we say the computed memory, it's not we say that we have a memory and DRAM and there another CPU connect close to the memory. We are talking about the way how we convert the memory itself can do the compute. So we'll start from chip level design, chip level, how the circuit is working, and then show how it's working and how the application are going on. For example, if we are looking on what type of functionality we want to do in machine learning, we need an architecture that can support 32-bit floating point, and one of the use cases is, for example, a neural network for learning. We need high precision. So this is GPU, as we know, and the CPU can do very high accuracy, and especially the GPU can do 32-bit floating point. We need also multi-precision. Sometimes we want to work on 2-bit, 4-bit, 8-bit, 16-bit, 32-bit, or sometimes we want to build a function that have 200-bit precision with 50-bit is the exponent of floating point. So we need this flexibility that this cannot exist in standard general purpose or GPUs. We need a performance for sort, search, for example, to find top K, give me 1 billion item, I have 1 billion item, I want to find what are the top 10,000. I need it very fast. For recommendation, for speech, to classify image and video. We need some time to do for heavy computational, nonlinearity, softmax, exponent, normalization. I go more explanation about those functionality, but this function we want to do in okay. And also we need to solve the bandwidth issue. Current solution of today is that we have a we have a CPU and we have the general purpose GPU, which is a GPUVS. It's connected to a very wide bus to external DRAM that limits the performance because the I/O, and it increases also the power consumption. But this is not scale if we want to do, for example, source search, or if we want to do function like a similarity search, not exact search, top K. It's very complicated to do that in this type of architecture. So if we looked here, we can see that this is the red is a GPU that it's very that it has very high performance in 30-bit floating point, but very bad performance in scalability in multi-precision. On the other case, there is some ASIC design or FPGA design that have more advantages in some cases, for example, a multi-precision. What I'm going to show you today is how in associative processing we can have we can improve, we cannot compete with GPU for floating point. We can, in a single memory chip, we can do 2 teraflops compared to tens of teraflops, but we increase significantly the scalability, searching capability, and also heavy computational multi-precision in associative computing. So how it's work? What is associative computing? Associative computing is a type of computed memory, as what you can see here. We call it APU, Associative Processing Unit. It's a memory. It's based on standard memory cell that it can do compute inside. I can do multiplication, addition, search, any type of computation. So the CPU just send the question, send the requirement to the memory, and the memory return it back. It's not a memory that connects to a small processor. The memory itself can do the compute. So how it works? Actually, computing model didn't change within the last 80 years. As we know, we have, I cannot, okay. As we can see here, this is a von Neumann architecture. Doesn't change even if we talk on the GPU parallel processing. We have we have the ALU. The ALU, okay. Okay, the ALU send a request to the memory by open an address. We can get the data from the memory to the ALU. The ALU do the computational and write back the answer to the memory. This is the way how it's work. But now let's see how associative processing is working. Actually, what is going on, here we have the memory, the same memory cell. We don't touch the memory. The memory is the same as a standard memory. We just change the address decoder. So instead of sending one address at a time and get back, we are fetching 2 addresses at the same time. So what will happen? If we have a bit line in the memory, we can read the data from the bit line. But if we'd like to read 2 values at the same time, one is 1 and the other is 0, we want to read 2 values at the same time, this sum looks like an error, but it's not an error. It is a NOR gate. So we are opening here 2 addresses at the same time and write it back. For example, if I have a memory and I want to write the value in address 5 and the value in address 10 at the same time. So if the value in address 5 have some number, and address 10 has another number, and I want to read them together in the same bit lines, there will be an error. Nothing. But it's not an error. It's a logic function, which call it NOR. Based on the Morgan law, if we have a NOR, we can do any type of computation. So all in the memory. So reading 1 location at a time, it's a standard memory. Reading 2 locations at a time, it's a 2-input NOR. 3 locations, it's 3 output NOR. So because it's a function that implement a NOR operation, we don't have to bring the data to the CPU. We just write back the data to the memory, and after several iterations, we can get the result. For example, if we like to do 16-bit floating point multiplication, we need about 80 times to do this transaction, multiple read and write. But if we have, because it's a memory, if we have millions of bit lines, it takes the same time, 80 clocks. Running in 1 gigahertz, we can get this very high performance computing. Now, after I preview that with the NOR gate, we can do any type of operation inside the memory. Let's see, and it is a standard memory. Let's see how we convert standard memory to do exact search, like to work as a CAM or ternary CAM, without adding external ternary count. The same memory, same SRAM, or any other type of memory, we should talk about it, can be converted to ternary count. Suppose we have a record, which, as you can see here in the left, and in the right, there is a key that we'd like to search in the memory. Instead of searching one address at a time, or instead of building or adding a new CAM to the system, which is very, very expensive, what we do, we just duplicate the data with one complement of it. We duplicated the key with also with one complemented, and here, when every place where is one is a key, we are opening the read enable in the memory. So if, as you can see here, all the read enable here looks read 0, and NOR of if all the input are 0, the output is 1. This is the logic function of the NOR. So actually we get the match here without adding any CAM, any contextual memory. So the memory can do compute by the logic and also can do search. We can do more on that. Suppose we have a don't care here. Don't care means it can be 1 or 0, and we want to search based on the don't care. Same memory cells, same standard cells, same memories that develop in the industry. What we do here, we convert the don't care from, we put in the range data, instead, all the don't care are represented by 0 in both cases. With the two scope, with the one's complement, it doesn't change. So it's 0 and 0. We are replicating the key value, and also again, where one opens the read enable, and we get match even in the don't care places. So to summarize this point is that we can have, if we have memory, every bit line in the standard memory now become a processor. We don't have to just take this bit line and connect it to another processor. Every bit line is a processor. So we can do any function based on the Boolean function. We can do any function between A and B, A multiply B, A plus B, etc. We have an ability to shift one section in parallel to the left or to the right, and they can do neighborhood operation, for example, a convolution for convolution neural network, or DCT, or FFT, or any type of neighborhood operation we can do inside. Also, because we have the exact match, we can do search. For example, 20, and it take 1 clock to get the responders, and we have also the ability inside the memory that is not explained here how to count the responder, and this also gives us the ability, if we know how to count, search and count. There's many applications for combination, for nearest neighbor, for random forest, and etc. Okay. For a database search and update, we have a memory, or the standard memory now, it's converted to be content-based search. We do content-based search. Right? Sorry about that. So, okay, we have its content-based search record can be placed anywhere. So we don't have to classify the data if we want to find later on, for example, the top K. We don't have to classify the data. The data can sit in the memory as is. We can bring any new record and put in the memory as is, because to search is take off one if it's classified or not classified. So it's very easy to arrange the data. So we don't have any time we're coming in new data, we have to rearrange the data in the memory. We can do exact match as CAM or ternary CAM. We can do similarity search. Sometimes we don't want to do exact match. We want to do something, for example, for fraud detection, we want to find some behavior of the data. So we need to do some search like L1, L2, cosine similarity, etc. So this is also can be exist in the memory, and we can do in-place aggregate. We don't have to bring, after we found the data, to bring it out. We can, it's in place. We can continue working on the data inside. Now it will look like if we take one standard SRAM cell, it's bit, as we know, it's 1 bit of cell. If we can take 2 bit, we can look at it as a 2 bit, as a 2 bit. Oh,
I think it's just having a sync, some sort of a sync issue. Just keep going.
Okay. It can be looked as a 2 bit, or 2 input NOR gate, or 1 TCAM cell. If we looked on 2 standard SRAM cell. If we looked on 3 standard SRAM cell, it can be looked like 3 memory cell.
I think it's...
Okay. Okay. 3 bit or 3 input NOR gate, or 2 input NOR gate plus 1 output, or 4 state CAM. All this type of combination, and etc. So if we compare CPU, GPU, and in-place, call it in-place computing, we have in CPU, GPU standard architecture, von Neumann architecture, we send an address to the memory. Here we search for a content. We don't have to send an address. The search, we can look by the content, don't have to look by an address. We fetch the data from memory and send it to the processor. In a associative processor, we just mark in place where we want to do the processing. In the CPU, GPU, we compute serially per core, and here we compute in place millions of data and at time, and also we don't have to write it back. Everything is done in place. If we talk on the architecture is based on many section bit lines that every section can do all this NOR operation and some communication between them. Actually, as you look, this is the layout of the chip. If you looked on the layout of, for example, of GPU or standard processor, you can see many blocks called them floating point block, arithmetic block, this and this block. Here, all is memory. This memory can do floating point operation and can do search, so all is based on memory. What is in the middle is just some ECC checking, control signal, etc. But all is memory, and this memory, all this circuit, it's members, it's standard SRAM cell that they can do a similarity search, non-similarity search, compute, any time of compute inside. So the same circuit can do based on the programming. Later we talk about how it's easily can be programmed. This is our first card, evaluation card. It has, which is going, we are tapping out the chip by the end of the year. Early next year, we're going to have some evaluation PC card that it have from precision, we can program it to be from 1 bit to even 160, 200 bit, whatever. 6.4 teraflops for floating point operation, up to 8 peta operation per second for Boolean algebra, because every bit line now is a processor and all can work together. So in a single card with less than 100 watt, we can reach to 8 peta operation per second in memory. So this is also we're going to demonstrate less than half a year from now. We can do a similarity search, top K. We can do it in all of one complexity. If we want to find, give me the top 10 or top 10,000, it takes few microseconds. It doesn't matter what is the size of K. In memory I/O, inside the memory cell, inside here, there is 2 peta bit per second internal bandwidth. It's order of magnitude that any other compute. And of course, sometimes we want to do for accommodation, it's just a sparse matrix multiplication. This be very efficient, can be implemented here. Okay, in APU server, this can be a single node, as we call it, or APU server. We have 64 chips or maybe up to 100 chips. So it's not 1 terabyte byte memory. It will be around in the range of 16 gigabyte to 20 gigabyte of associative computing. It has to be to read data from DRAM, but when the data is something in between. So when we bring the data inside, everything can be done. It can be done in compute. Of course, the performance is 32 petabit per second I/O, and etc., up to 128 tera operation per second in a example application. If we talk, for example, we want to find, give me a top K. We have in these examples 36 samples, 2 dimension here, X and Y, divided to 3 group, and we want to find the yellow one to which group it belongs. So if we say, for example, give me K equal 4, I found it's 4 nearest neighbor, and then say that, and see that the green is a majority and the green is selected. In the real life, what we can do, we can take our associative memory, and if you have millions of items, each item is not only X, Y, 2-dimensional. Sometimes there are 100 dimension, 200 dimension. We are embedding all this database inside the memory, and inside the associative memory, all this data, and then we send a query. The query is also also can be the same dimension, number of dimension as the same number of dimension as the data, and we distribute the data in the memory. It takes 2 clocks to distribute the data in the memory. It's not just write by address. We just, if you have a data in associative memory, you want to write in a data, we can distribute in 2 clocks to every place which we want in only 2 machine cycles in the memory. Then we want to do some operation. Here in this example, we want to do some cosine similarity between the yellow and here. We do for every bit line now with the processors that implement this type of function. So any type of function we can put here. This is similarity. It's not exact match. If you want exact match, it may be 1 clock. If it's cosine similarity, it take a few hundred clocks. But it depends on how many clocks. And then we, sorry about that. It's not. And then we get the responder and find the top K. Top K can be also of one complexity, and find the majority and get the result in the memory. So this type of memory in associative memory is the fastest architecture that can give and solve this K nearest neighbor and do similarity search in orders of magnitude faster than any other GPU, and all again inside the memory. Okay, so we can also handle billion of record and find top K, let's say top 100,000 very efficiently. So now if we want to do search, if we take now any type of signal, if it can be image or text or speech or whatever, we have to do some feature extraction to the data. For example, to do the image, for people with knowledge in deep learning, we can do some convolution layer of the data, so we can generate any image to feature. Every image we can generate to tens of feature based on the convolution layer, and we put all these images. Suppose we have 1 million image, 2 million images in our database. We can embed them in the memory. We can also take a text. We can convert it to bag of word, word embedding, sentence embedding, and then we do the search in the memory. Just give you an example how we do in OF1. We can do the top K. Suppose we have 1 billion number, and we want to find, give me the top 10,000. What we do? If you look at that, I'm not going to show all the details, but if you looked on all the data, we have here, for example, 1 billion items, or let's say 1 million, anywhere. It's sitting in associative memory. Now, if we looked on only in parallel on the most significant bit, all of them, so all which are 1 are candidate to be max. All which are 0 are not relevant. So I do some markering and start from the most significant bit to the least significant bit, do some computation with this mark, and by the end of the day, I get the top k here, which is 4, for example. I wanted to find 4. So it depends on the precision. So it doesn't matter when I say of one complexity, it doesn't matter if I want to search k equal 10, k equal 10,000. Or also, that it's also doesn't matter what is the size of the memory if all the memory is sitting in the associative, all the data sitting in the associative memory. Sparse matrix multiplication based on associative computing. If we have an input vector, and here we have sparse. So actually, what we are presenting here, as you can see here, the value number. We take the C sparse. It can be 1 million by 1 million, 1 billion by 1 billion sparse. We are presenting the sparse by a table set in column number. The value 3 is belong to column number 1 and row number 2. So we are presenting the sparse inside, and now based on search, we bring the value here. We are searching all column row equal 2. We are searching where there is 2 here. Here's only 1, 2 row, so we do search similarity, not similarity. We do some pattern search here. We found 2 and bring where 2. So bring the input value to row number 2. Then we can do to all of them, and after that we do the multiplication in parallel and get the result of n plus log beta, which is very, very, very fast. Now let's go to talk a little bit on natural language processing, which has become very, very important in question and answer and dialogue, language search and speech recognition, etc. How we do that? We are actually we would like to learn things from the past. To do that, we need a memory. For example, if we have the sentence, For example, if we have the sentence, Dan puts the book in his car, and there is a long story, let's say 20 pages, and then Mike took Dan's car, and then also there is a long story, and he drove to San Francisco. And I want to ask the question, and all this story is in the memory, and I want to ask the question, where is the book now? I want the system that the memory will answer car San Francisco. So in order to do that, there is several architecture. I'm not going deeply here, but this is developed by Western in Facebook. There are many other architecture. But what we see here is that here the blue one, what they do some machine learning and they took every sentence and do a sentence embedding. So every sentence is represented by a feature map. For example, Dan took the car. It's represented by 200 feature number. Dan eats the milk. Another feature map based by deep learning. So this is the blue. This is all done by deep learning. And the yellow is what kind of answer for this sentence. Now, I took all these sentences, embedding this in associative memory, and what we have to do, now there is a question, where is the book? So we take this, we have to take this question, we convert it also to a feature based on machine learning, do a cosine similarity to the green one, and then we have to do some type of softmax, is to do some prediction. What is the chance that the answer will be in one of the places? The yellow is a type of answers that can be generated from this specific sentence. And then I have and then I multiply this softmax by the value, do some weighting average, and look for candidate to find what is a result which is needed. A requirement for in-memory compute is that we need a memory that we can embed feature in the memory. This is one of the requirements. We need to do a function like a softmax. We have to do some vector multiplication inside the memory. We have, as this is the constant similarity, we need to do softmax. Softmax is the function which is the exponent. We have to do the exponent of each one of the items divided by the sum of this exponent. So we cannot, it's not just an exponent. We have to, it's normalized. In order to normalize, we have to find the exponent of all the value in the memory. So until we finish to do the computed, the first exponent, all the data, then we have to do the dividing. So actually, we need this type of memory. It cannot be done in GPU. And also, we have to do some vertical multiplication and get the output. And this is schematics of the associative processing that have the capability to do that. We can broadcast. This is function which represents associative memory. Broadcast data. We can take any data and broadcast it to the memory where t is equal 1. So if t is equal 1, we can broadcast the data only in places where they are marked by 1. So we not broadcast to all the data. We just want to do selectivity broadcasting. Then we can do Then we can do the compute in this direction and also generate output by this direction to do the summarize and this way. And show you here how we're embedding inside the associative memory the key and the value, and we can do inside the softmax to implement this network for a natural language. A programming model. If we have, we can write an application in C++ or with Python. There is framework right now with TensorFlow. TensorFlow is more machine learning oriented. It converted to a graph execution and then it's run on the APU. For example, this is a function if you want to do some multiplication with TensorFlow. So this is, we take Tensor A, Tensor B, and we can do the multiplication. But because also it's in memory, we can do, if we have, for example, we want to do multiply between C equal A plus B, and then we want to find what is the top K, because we are in memory compute, and also as a TensorFlow support graph execution, we can combine this function together in memory, which called it fused, that we can do multiply and top K. What we gain here, because, for example, if you want to do vector multiplication of, let's say, millions of number, then we want to find the top 50. So why we lose a lot of power consumption? Why we do so much multiplication, and by the end of the day, we want to choose only 50 numbers? So here, if the data is inside the memory, we do the multiplication in a way that we start, for example, multiplication with the most significant bit and start removing data which is not relevant, and we don't do the multiplication to all the data. So every step we do multiplication in less and less in the data because we manage in the memory, and this way we are saving power. The next slide is showing where we are going, the future research. Actually, this is, as we know, HD, flash, and then DRAM, L1, L2 cache, and CPU register file. This is a hierarchy of the memory. we believe that associative memory will be something here in between. We are right here now. By early next year, we're going to have this SRAM that do compute, is something in between. But our technologies that we can do, we can read multiple address at the same time when it gets the NOR operation of the bit line. This work on any non-volatile memory. It can work on ReRAM, it can work on PCRAM, it can work on STT-RAM, any non-volatile memory. So by the end of the day, we can have billions of processors inside the storage itself. So, but here in the flash, there is endurance problem. We cannot do some computation right back to the memory because the endurance. So we are PCRAM and ReRAM and flash has a bad endurance. And here, as you go up, we have better endurance, we don't have endurance problem. So in memory, which we have more endurance problem, we do mostly search and not compute. As long we go here, for example, for STT-RAM, ReRAM, that not suffer from endurance, we can do compute. So this is the roadmap for the next 10 years, but actually we are starting now with the SRAM. Okay, thank you. You have here, it's a software architecture. Yeah.
When you talk about memory in your APU, what's the cell type of the memory? Is it SRAM?
It's SRAM based, yes.
Okay, it's SRAM.
Yeah, yeah.
Standard SRAM.
It's standard SRAM. So today it's standard SRAM. Tomorrow it will be non-volatile. But now we're starting with SRAM. Yeah.
Now, how about use this model on the DRAM? Do you need any specific?
DRAM, it cannot be used very well in DRAM because the DRAM is destructive data. If you read two values at the same time, you need a sense amplifier to correct the data. So it can work on SRAM and non-volatile memory. In DRAM, there is another way. In DRAM, you can buy after the bit line, after the sense amplifier, you can add some SRAM cell to do that. But this cannot work well in DRAM. We believe in SRAM and non-volatile.
So it's basically the cell that comes in to be remain static.
Yeah, yeah. It's a standard static CMOS technology, TSMC compliant. So standard 60, 80 SRAM, yeah.
Early part of the presentation, so sorry to ask you this question again. So you're building a processing unit embedded with lots of SRAM. Is that what your product?
You want to add? Yeah.
I think the basic idea is there is a processing unit, but the memory itself is the processor. In the layout that we showed, there were 4 ARC cores, but they're just basically the controllers. You've got to think of the memory as the processor. And that's really what's providing teraflops of data or orders of magnitude more such capability.
So if somebody wants to use your memory or the processor, how does it fit with the current server? Is it on the PCIe or the DDR4?
It's a standard PC. Our first product will be a standard PCIe plug-in card that you put it in just as you would put in your GPU. If you're doing machine learning framework, for example, and then we provide the TensorFlow framework. So as far as you're concerned, you can run the same. Your server can run the same TensorFlow code written in Python. In fact, TensorFlow will allocate different functions to different hardware. So say you've got a CPU, Xeon say, and a K80 GPU and our board, it will allocate it among them. And you could, if you don't want to think about all the theory that Avidan's been presenting here, you can just look at it as something that runs your sorts and searches orders of magnitude faster, your GPU, your floating point functions similarly, and other than that, continue as you are.
Yes.
So it's basically your APU is mostly SRAM memory
Yeah.
with some control logic.
Yes, if you
Yeah,
remember
yeah.
that layout, there was just 4 tiny little blocks of control logic. The vast majority, 95%, is basically SRAM memory.
Yeah, inside the chip, we didn't go into technical detail, but inside the chip were 4 ARC small processor that manage the associative processors.
Okay. So then the size of that APU, what's the biggest size you can put in?
In memory?
Yeah, in the memory.
Okay, it says that in a single chip, but it's a very small chip, it's about 20 megabyte. We think in a server, we're talking about in a server, we can have in the range of 16 gigabyte of SRAM. So if you have a server, for example, 1 tera memory RAM, and you have a CPU, so you can put just another server in the middle, in between, that can do with 16 gigabyte of associative memory in the server.
I think
What you say your interface right now is going from that APU to the server is GSI'S, right?
Yeah.
But quotation could be like a memory interface.
No, there is also inside the
sorry, in our roadmap, the current implementation is not designed, chip is not, say, a memory chip as such. The right way to think about today's offering is as a coprocessor, just like a GPU. But in our roadmap, we will actually be producing more DRAM-based memories that will be JEDEC compatible. So you actually insert that as a regular DRAM chip. It'll have more memory, less processing capability, but it'll be in other ways totally transparently memory.
So this is just the accelerator. It happened to be used ASMENT as the key technology.
Yes, except that it's also holding the data as such in time. We had a question over here, yes.
This is processing in memory. First of all, PIM, P-I-M.
Yeah.
And you're not the only guys working on this. The other thing is that where do you find, you put resistive RAM on the very bottom. And there's been some really interesting progress on the durability of CB RAM expressed through lately. In fact, it looks like it's going way over 10 million writes. In fact, it may be 10 to the 15th. Where does that durability question end up in something like this?
I think that the durability issue, if you're doing intensive compute and the data is going backwards and in and out the whole time, it becomes an issue. I think that we haven't yet gotten around to those products. It's theoretical capabilities. What we would have to do is stage or build up a pyramid of some kind so that, 10,000 writes, 10 million writes might not provide you the lifetime that you need, unless most of that data is not your actual workspace, your actual execute right.
NRAM could be included in that column.
Yes.
yes.
This roadmap represents, except for the DRAM thing, more where we can go. The same architecture, the same concepts will hold through into the deep future as the basic memory technologies replace what we have today. We see things only getting better.
Really don't care what the technology is of the memory device as long as it's not destructive.
Yes, any type. If in 50 years from now, a new type of biological memory, if it's non-destructive, it should work.
In terms of discriminating between the different types of non-volatile memory there, you're basically calibrating it based on the amount of endurance that they can do, and that will
Yeah.
equate to some of the functions that you're able to do. But isn't that, couldn't you bring in more functions even with lesser endurance, or I guess...
Yeah, I think for example, with which I say read most of the time. For example, here in RAM-based PC RAM, it's we call it mid endurance. We do, for example, malware detection because we have to do a lot of cosine similarity, lots of read operation. We don't have a lot of write there. So this is mid endurance. So, for example, in this type of PC RAM, for STT RAM, I think we can do most computation right back, matrix multiplication, most of the computation.
Extremely low-cost inference engines for the low-end processing market or controller market. That would be a ready-made solution.
Yes.
Yeah.
An inference engine that's more of a ROM. It's just made to see certain things, let's put it that way. It doesn't have to write.
Yeah, yeah, it is. Yeah, here, for example, it doesn't have to write. Cosine similarity search, yeah, we don't have to write on type of database search. But if we want to do some machine learning intensive operation that need to read or write in the memory, we can do. We have to do that. But actually, we start with the SRAM because there's no risk right now, and there's a lot of marketing potential for this type of product.
I'll make a comment here, is that a lot of people in the embedded control market haven't caught on to the idea that you can use these engines as a multi-input decision maker. Instead of having serial spaghetti code waiting for each event to happen in serial mode, the events are happening in parallel, and you can do the decisions in parallel. This is absolutely something new in the world of embedded control. They just really haven't caught on yet.
Sounds like we should discuss this in detail and hear your thoughts. Yes?
One more question. Have you done any analysis comparison with, for example, VBS?
Yes, of course. Yeah, of course. Floating point operation, let's say we, in a single chip of us, memory chip with 2 teraflops compare, let's say, to 8 teraflops of standard NVIDIA. But it's a small memory chip. You can connect in about tens of that. But this is it. But on other case, if we want to do, for example, top K, for example, we are more than 3 orders of magnitude, the softmax search, multiple precision, 1-bit operation, 2-bit, 4-bit, 8-bit. We are order of magnitude than TPU, CPU, GPU. We are only the same level of floating point, 32-bit, 16-bit. But in all other cases, for example, search, nonlinearity, what else? Yeah. Okay.
How different is your product compared to FPGA? Because they are already SRAM-based designs.
It is more generic than FPGA because FPGA is logic that you connect between the logic. Here, the basic instruction is read and write, is a memory. So there's one customer that talked to us, I want to do floating point of 1,000 bit. I want the exponent will be 200 bit. Can you do that? Yes, we can build it as a microcode here. So there is a lot of flexibility here because the basic instruction, if you looked on our microcode, if you do deep learning, convolution, natural language, the basic instruction are read and write.
Can I just add to that answer? If we're just comparing it to FPGA, the specific advantages are that FPGA does not provide you these search capabilities, and when talking about basically programmable ASIC level power and speed capabilities. So when you combine that, even if you're doing something that theoretically you can program a 3-bit multiply into an FPGA, you're going to get a power performance advantage again of orders of magnitude over the FPGA. But on the other hand, it's the FPGA and us who could actually do it in the first place. Theoretically, you could also do it in a CPU, but
Yeah.
you wouldn't want to.
Here is a slide of showing the differences. As I read, you see this is the GPU. GPU, this is NVIDIA very good in floating point operation, but floating point operation, you cannot do good search if you do floating point exact search, malware detection. They are very good in floating point operation. It's targeted to do machine, yeah.
Yeah, how many bits is that floating point?
Here is 32-bit.
32 bits. Well, a lot of people think you can do multiplies in 4 bits and get away with it just fine.
We are here in 4-bit.
Yeah.
Here's Linear. We are here in 4-bit. With 4-bit. In 8-bit with something in between. 4-bit. In 1-bit, with a single chip, 2 peta operation. Peta, not tera, peta. If you took 1 bit. Sort search, this is non-linear scale. This is 1,100. This is orders of magnitude. Here, sort search. Here, this is FPGA.
Yeah, in sparse data representations, you don't need that many bits.
Of course.
The world just doesn't know it yet.
Yeah, but I want to show, to be fair enough to the GPU, so I said I cannot compete the GPU with 32-bit floating point. But I cover many other.
My point is that 32 bits is way too many bits. You can get away with 4.
We agree.
Yeah. And if you looked on GPU.
That means you can raise your own number.
Yeah. If you looked on GPU layout chip, you see a lot of block of 32-bit floating point, 16-bit, a lot of block. Here, our layout is a memory. I can do floating point, I say 1,000-bit floating point. You cannot do it in a GPU. But some customers that want 1,000 floating point, they need this accuracy. We can do that. So, so here, tapping out, now we're working very hard, tapping out by the end of the year. Early April, March next year, we'll have the evaluation cards. If you're interested, you can.
So do you have partners that you're in business with?
We are talking with partner, yes.
When will we know more about this?
Pat will like to answer. The Pat is our marketing director.
In terms of a general product announcement,
Yeah, GSI is not a really big outfit, so to speak, right? It's not an Intel or Micron or anything like that. So we're wondering, all right, the wonder is you know, where's the traction here?
so I mean, obviously behind the scenes, we're talking with all, we obviously can't say who, but in every application, especially machine learning, you're talking about those guys that you can think of. Okay, so we have traction with those guys, that's what we're working with. In terms of announcement, obviously what we want to do is we're waiting until, honestly, tape out. We want to do a little more and ship back to make a general announcement. We have announced it on a lower scale. We just haven't really made the big announcement.
Yeah, I've gone through all your stuff.
Okay. Yeah, so what you're going to see, we're actually going to be starting putting a lot more papers, for example, on top case. So we're going to try and do specific papers. So we've been getting feedback from customers. Hey, we want to know softmax. What's your top K performance? We're going to do those first. Then start to announce it more. Okay, this is how you use it for natural language processing. But right now it's more, I mean, we're working honestly behind the scenes with kind of the research guys and all those companies. That's how we're doing it.
One question I do have is that with hyperscale applications, everybody wants it for one, free, low power, really low latency as possible. They want everything, all right, that really can't be delivered all that well. But the other thing they want is they want it to be, they want to be able to apply it to all the general questions, so to speak, in computing. And now we have this this new computing called processing in memory, if you will. And you know, there's more ways of skinning this cat, but let's just suggest that we have a general case here, and you're showing a better way, lower power, to do it. How do you feel that the hyperscalers are going to look at this?
I'm not quite so sure what you mean by the hyperscale. I don't mean. Can you explain what the hyperscale is?
The hyperscalers, obviously, if you look, search is a key component, intelligent search, natural language processing. So all the hyperscalers are talking about, I mean, right now, they're all doing computing translation. That's all machine learning. So from the hyperscalers, the
Okay, let's continue that discussion.
Yeah, there's many ideas. That now we're more focusing on machine learning, but many ideas.
Okay,
Okay.
thank you
Thank
very
you
much.
very much.